doing it.
Connecting.
Great, thank you.
So can you still see my screen?
No, you
No.
you probably have to get it back.
Right. Okay. So now starting the recording. So to summarize what I was saying so far, I'm saying that there are many different opportunities in formal methods, but in general, if you want to try out some of these nice ideas, you need to have a formal account of the system, of the software, wherever you are considering. So there is a central element here, which is the formal definition, the formal model of the artifact of your interest. And in this scope, we are going to have different tutorials covering different parts of this field. For instance, Serge is going to speak more about model checkers. And I'm presenting this picture to put what I'm going to explain next in context. So in the next hours, I'm going to show you in a very practical way one proof of system that is a tool that you can use to formalize properties and then prove these properties using some machinery, right? If you have any questions, please do interrupt me. And similarly to Anna, if you want to make the questions in Portuguese for free, I can then translate them to English to the other people. If you are someone starting in this area, I would strongly recommend you to read these two papers. They are very recent papers that give a very nice overview on the formal methods area. Okay, so this is the end of my slides, and as I said before, I'm going to be very practical here to show you some nice things. So let me stop sharing the slides. Right, and now you should be able to see the interface of the Coq ID. Is this font too small? Is it fine? Okay.
It's fine for me.
Great. So what is the main learning outcome from this talk? I have prepared this talk thinking about someone that has never used proof of systems before, probably, that would like to have some idea, some general idea of how you can use this tool called Coq to formalize properties and then prove that these properties hold in a particular implementation of some software. So Coq is what's called an interactive proof of system. It has been developed since 1984, so it's not something entirely new. And it comprises some languages. So it has a functional language called Galena, which is very similar to Haskell. It has a language that you can use to create proofs. So basically you have tactics to develop proofs. And you have a language called LTAC. That is a language that can be used to define new tactics. So basically can create your own customized tactics to target specific domains and to reach some level of proof automation. There are many interesting applications of this proof of system. Particularly, there is a project called DeepSpec, which is an expedition, according to them, in computing, funded by the NSF in the United States. So if you have never heard about this project, I recommend you to spend some time, look into their webpage. I have some interesting information how you can use formal methods in practice, particularly using Coq as a foundation for this. I will share these files right later. I will send them, I think, in the Discord respective channel. So that you have here some links for the official reference manual, and particularly this very nice series of books, the Software Foundations series. So now it's a series of 6 books. There is a first one covering logic foundations, all of them in the context of Coq, and some more advanced topics on separation logic, on how you can use Coq to verify the correctness of some classical algorithms. And the book is free, and the material is available online. And recently, they have also deployed an online website for running Coq. So you can go through the book online and simultaneously executing the book, executing the commands embedded in the book. And there are other classical books on Coq as well. So this talk has 2 parts, right? So this is the first one, then we have a break, and then the second one. The second one, for the second one, I have written a concrete example of how to use these concepts to prove that an implementation of a dictionary that uses binary search trees satisfy a set of properties that have been formally specified. But before we get there, I need to explain to you some foundations, some important parts of the Coq universe. So in this first part, I will first present this language called Galena. If you are familiar with Haskell, you will probably understand almost everything. There are some differences, but you get the main idea quite easy. I will get some time showing you examples of the proof language supported by Coq. So you will see how this idea of writing theorems and using a set of tactics to prove a specified goal, how this works. Then I will talk a bit about logic in Coq in a very practical way. And then I will conclude this first part illustrating the differences about functional, logical, and inductive definitions. So in many situations, the same concept can be defined in different ways, and there are pros and cons depending on the way you choose to specify these. One last thing I would like to say before getting to the practical part. This project, the DeepSpec project I mentioned before the pandemic, they used it to organize a summer school, a very nice summer school where you use it to spend 2 weeks running these tools for the whole day. Well, I hope that in the future, so from the thinking about linear temporal logic, so F, sometime we will be able to get back to these summer schools. So they were very interesting. So right, first I will talk about Galena. So this IDE, you have comments, right? And you have code that needs to be written in some of these languages supported by Coq. So you can, as most functional languages, you can define new types. And these example that has been extracted from the logical foundations. you have a definition of a day. So when I ask the tool to process this document, this file up to this point, this green highlight says that all the text, all the definitions up to this point have been processed and they are okay. Okay, so this first definition is basically defining a new type called day, and you have different constructors that creates an instance of a day. So you can read each line as Monday is the name of the constructor, the name of a function that takes no arguments and produces an instance of a day. So besides defining new types, you can define functions. Well, it's a functional language. And here you have a very simple example of a non-recursive function that is defined using partner matching. So the function next weekday takes as input a variable d, which is a day, and it outputs the next weekday. So it performs partner matching in the value of d, and depending on the constructor that has been used to create d, it returns the next weekday. So pretty simple. I may say that the keyword definition is used when you are defining non-recursive functions in Galena. You can use this command called compute to evaluate expressions in Galena. So I can say, I can write compute this expression, evaluate this expression. That means what is the next weekday after Friday? So when I execute this command, you see here in the bottom, the output produced by the computation of this expression. So in this case, the output is Monday. So the next weekday after Friday is Monday, and Monday is a value of type day. If I write the next weekday, so the weekday after Saturday, the output as expected is Tuesday. So the day after, the weekday after, the first weekday after Saturday is obviously Tuesday. In Coq, you can write examples that can be seen like theorems or lemmas, but basically there are no semantic distinction, but we usually use the keyword example to encode something like a unit test. So I expect that this expression, when evaluated, will be equal to the value Tuesday. So when I enter, when I process this definition, so this example, you can see here that in the top right of my screen, I have a goal, which is something I need to prove. So I want to prove that this expression is equal to this one. And then you use the keyword proof to enter in proof mode. So basically this keyword says, right, now I'm going to start writing commands from a different language, from the proof language of Coq. I'm not going to explain the tactics at this moment because I will address this later. But just to conclude this first example, here I'm invoking the tactic reflexivity that is enough for proving that this equality holds. And since I have nothing else to prove, I can conclude my example. So as I said before, you can see this example as a unity test. So you can write, if you are creating a specification, thinking about a test-driven approach, you could write first the examples you want to, that should hold, and then you provide the body for your definition, the definition of a function, and then you test whether the provided definition makes all the examples true. Well, we can create other types like booleans. So basically, here I'm printing the definition of the type bool from the standard library of Coq. So bool is a type with two constructors, true and false. So it's true and false, not from the logic, but the Boolean value. And then you can create classical functions on Booleans, like the Boolean negation. So it takes a Boolean and it performs pattern matching on B. So if B is true, this function returns false. And if the input is false, it returns true. So pretty simple. And then you can perform computations on these definitions. So you can just check that the negation of the Boolean negation of false yields true. And the Boolean negation of true yields false. As you would expect, you can define functions that take more than one argument. So here I have the definition of the Boolean end. If the first Boolean is true, the output of this function is a logical value of B2, right? If the first one, the value of B1 is false, considering the idea of short circuit, we know that the output will be false regardless of the value of B2. So you can define or B in a very similar way. You can define functions using nested partner matching. So here's definition of the not and B. So you can nest the partners. You can perform multiple partner matching in a single level. So here I have a different definition for not and B, where I'm matching the values of B1 and B2 in the same level. Okay, you can define functions reusing definitions of all the functions as expected. So nothing too complicated or probably new so far. You can model natural numbers using the idea of having a base case, so a 0, and then providing a constructor for generating all the natural numbers using the idea of the successor. So here, the difference, what is different here is that the type NAT has two constructors, but note that the second one takes a natural as input. So the first constructor O, it receives no arguments and it delivers a natural number, whereas the S constructor takes as input a natural number and it delivers a new natural number. So Coq has already embedded in its core some machinery for converting O to 0, SSSO to 3, and things like that. So you can write the numbers using digits, but it can internally convert them to this kind of representation. If you are someone already in the community, you may know that there are other more efficient ways of representing natural numbers that are also supported in Coq. But I'm not going to get into the details here. So from now on, I'm importing from the Coq prelude, so from its base, the definitions associated with natural numbers. So you can define functions like the predecessor of a natural number, again using partner matching. So the predecessor of 0 is 0, and the predecessor of a number n, which is a successor of a n prime, So the predecessor of this n would be just n prime, right? So as I said before, constructors are functions. So if you use this command check, this command outputs in the console the type of a name, of an identifier of a function, or of a variable, or whatever. So in this case, s is a function from a natural number to another natural number, the same situation as the predecessor. There are some differences between them. We say that predecessor is a computable definition, whereas S is not. But I want to stick here to the general idea instead, getting to the very details. Right. Coq has a specific keyword if you want to define recursive functions. And the keyword is fixed point. So here you have a definition of a function that tests whether a natural number is even. So if n is a number constructed with the constructor O, so 0, okay, 0 is a natural number. The successor of 0, so 1, is not a natural number. And to check whether the successor of some n prime is a natural number, it depends on whether n prime is a natural number. So here is the recursion. And this recursion will, at some point, lead to one of these two basic cases. And Galena has, here's one difference between Galena and Haskell, is that when you define a recursive function in Coq, Coq needs to be able to identify that that function will always terminate. And this can be done. So the most simplest way of doing this is letting Coq infer this. And basically Coq will check whether the recursive call is performed on some term that is structurally smaller than the argument received. So here, since in this situation, where I have the recursion, since even b is applied to n prime, and note that this term is structurally smaller. I mean, you have less constructors applied to it when we compare to this one. As a side effect, we have the guarantee that this function will terminate. So that's the reason why you see in the console this message that even b is recursively defined and the recursion is guarded on the first argument. Okay. In more complex situations, you can provide by yourself an evidence, a proof that a function terminates. This is useful when this automatic mechanism of Coq cannot infer that the function will always terminate, right? But this is a strong requirement of Galena. All defined functions must terminate. And the underlying reason is that these functions will be used in possibly in theorems, and you don't want to carry to the theorems the need to worry of, is this function, is this term well defined in the sense that the computation of this term will end? So you need to provide this evidence that all recursive computations will end at some point. Right. As a functional language, you have support to these typical ideas of lists. So here I'm importing the definition from the library. I'm importing some syntax sugar, so you can write lists using these symbols instead of referring to the constructors of the type list. So as many other functional languages, you can define polymorphic types. So here you have the definition of a polymorphic list. So the type of the list is a parameter of the type list. So we have two constructors, nil and cons. So nil is a constructor that uses, the idea is the empty list, and cons is the constructor that takes an element of type A, a list of elements A, and it yields a bigger list, placing the value A as the head of the new list, right? So in these list notations, you have, there is a keyword in Coq called notation, where you can define syntax sugars. So for instance, if I write here, locate the definition of this symbol, it will say, okay, this notation is a syntax sugar for this expression. So instead of writing cons x, y, you can write this, okay? And in the library, you have built-in definitions of the classical functions for lists. So you have, for instance, the function, a recursive function called repeat that provided a value x in the natural number n. It yields a list with size n where all elements are equal to x, right? So you can, for instance, write a test that repeat 4 two times yields a list with the number 4 occurring twice. They can use again the tactic reflexivity to finish this very basic proof. And since the list is polymorphic, you can create lists of any type, not only lists of natural numbers as expected. Galena also has support for higher order functions, so you can define functions that take as arguments all the functions. So a very classical example is the function filter. Here I'm printing the definition from the library. So filter is a recursive function, so it's a fixed point. It takes as argument a value, the type a function from A to O, and the list of elements of type A. And basically what this function does is it recurses on the list, and for each element of the list, it applies the test F, and if the test holds, that element is kept in the output. Otherwise, that element is not kept in the output. So for instance, if you write filter this list, considering the function even b, the function even b will be applied to 1, 2, 3, and 4. And the output will be the list containing only the numbers where this function yields true. So the list with the natural, with the even numbers. So in this case, the output is a list with 2 and 4, right? You can also write anonymous functions. So there is this built-in function called EQB, which is the equality comparison concerning the Boolean equality. So this function takes as argument two natural numbers and yields a Boolean value. And you can write expressions where you have anonymous functions applied to the list in this case. So as I said before, if you are familiar with some functional language like Haskell, it's very similar to what you have been probably seen before. Do we have any questions so far, or are you fine? So if you're fine, let's continue. and get into the part that is probably new to some of you. So let's talk about the proof language supported by Coq. So now we are going to write theorems. So we are going to define propositions, and we are going to use this proof language to prove that these propositions hold. So for instance, I have here a very basic one that says that for all natural numbers, if you add 0 to this number, the output is equal to n, right? So as I said before, you use this special keyword proof to say that you are entering proof mode. And now you're going to provide the IDE with commands from the proof language. And these commands will modify your proof goal and your proof context with the ultimate goal of reaching true. So to prove that this goal, that this proposition holds. So there are many different tactics supported, and it takes time to know most of them and to get used to them. So in the following examples, I will cover just some of them and specific applications of some of them. So the first tactic I'm using here is intros. So I have a predicate to prove, which is universally quantified, and the static intros perform universal instantiation. So instead of proving this, when I perform the static, I say, okay, I want to prove this proposition for an arbitrary n, which is a natural number. So in the proof context, this tactic is responsible for getting rid of the universal quantification and moving the variable that was introduced by the quantification to the context. So what you see above this bar here is the context of this proof. This symbol plus is a syntax sugar. There are many syntax sugar for plus, but in this context, so in the scope of natural numbers, this symbol is a syntax sugar for the function add. And if we see the definition of add, we note that add is a recursive function that takes two natural numbers as argument. And if the first one is 0, it outputs m. So that's the value of the second argument. So if we consider this function applied to these two arguments, we see that the first argument is 0, so it matches to with this partner, and the output is going to be n. And there is a tactic called simplify, which performs simplifications on the proof goal or the proof context based on the definitions you have. So when I execute this command, you see that my goal changes from 0 plus n to n. And in that point, I have an equality, a trivial equality that says that n is equal to n. And I can disprove using that tactic I mentioned before, that is reflexivity. Okay. Actually, reflexivity is a quite complicated strategy, and it calls simplify if it helps. So I could just have written reflexivity, but these are some details. So that's one possible proof style. You perform proofs by simplifying terms until you reach a trivial equality. Another possibility is performing proofs by rewriting terms. So there is this tactic called rewrite, where you can use hypotheses from your context or from the library, so previously proven theorems, to rewrite some expression in the proof goal or in the proof context. And this arrow indicates the direction of the rewrite. So here I say I have a different theorem that states that for any two natural numbers, if they are the same, n plus n is equal to m plus m. So here I perform universal instantiation, and note that I have a hypothesis to prove this goal. That is, I'm assuming that n is equal to m. Because if you remember your basic classes on logics, when you have an implication, if the antecedent is false, the proposition is true by definition. So you want to prove that this expression holds, assuming that this hypothesis also holds. So in this case, I can write the common rewrite from the left to the right using the hypothesis H. So in this situation, what it's going to do is it will replace in the proof goal all occurrences of n by m. So when I do this, I'm left with this equality, which is trivially true. Okay. So depending on what you want to prove, this can become more complicated. So you may need to perform many rewrites during your proof. That is the case here, with the goal of reaching some trivial equality. You can also, as I said before, you can also use rewrite using previously proved statements. So suppose that you want to prove this equality here, considering these natural numbers. You can, for instance, use this very nice command called search, where you basically ask Coq to do a search in its library, looking for previously proved statements where you have 0 plus something. And when I do this, I find these previously proved statements, and I can, for instance, rewrite my proof goal reusing this theorem that has been proved before. Okay, so this is something that's also possible in Coq. So I have already talked about proof by simplification, proof by rewriting. Another very a typical situation is performing proofs by case analysis. So here I have a different statement, and you can see that if I perform simplification, it doesn't work because the partner matching is not very clever. For instance, it says that if the left term is 0, it simplifies, it can simplify to m, but not the case here. So simplify does not help in this situation. So I'm aborting this tentative proof. And here I have the code, the proof script that works. So basically in this situation, you need to prove this statement using case analysis. So the idea is you have n, which is a natural number. And if you recall the definition of a natural number, you are going to see that there are only two possible ways of creating a natural number, or using the constructor O, or using the constructor S. So when you perform a case analysis in this situation, you are creating two sub-goals. So assume that n is 0, and in the other sub-goal, assume that n is the successor of some arbitrary n prime. So this tactic called destruct performs this kind of case analysis, and I can provide to it the names of the arguments that are going to be used by the underlying constructors. So in this case, as I said, when I perform this tactic, I'm left with two sub-goals. The first one, n is 0, and the other one, n is a successor of some n prime. In this case, the previously seen tactics work fine. So you can perform a case analysis on Boolean, so you can use this idea to, okay, I want to prove that the Boolean negation of the Boolean negation of a Boolean is equal to the value of this Boolean. So you can say, okay, perform a case analysis on B. So B can be true or B can be false. And then you can finish this proof quite easy. And you can perform multiple case analysis. So in this situation, I want to prove that the Boolean n is commutative. So, okay, I want to consider all possibilities for B and C. So as a consequence, I'm left with 4 subgoals with all possible combinations, right? Okay, I forgot to mention, but this symbol here is used to focus on a specific subgoal. Actually, the next one, right? So you could have written like this, and it will show all subgoals at the same time, but you can use this minus. Okay, I want to focus on the next one. Please show me the information just about the next one. And as expected, you also have support to perform proof by induction, right? So suppose that you want to prove that it's a statement similar to one that has been proved before, but the difference is that and since me, can you hear me? I have just gotten a message that my internet connection is not stable, but this is fine. Okay, let's continue. So simplify does not help here because it cannot perform simplification due to the pattern matching, because the pattern matching is performed considering the first argument, and the 0 here is the second argument. Case analysis is also not promising. So if you try to prove these statements using case analysis, you will eventually go back to the initial step. So that's a situation where you need to prove this by induction. So as you know, you have a base case, which usually can be trivially proven, and then you have the induction step, and now in the context appears the induction hypothesis, and then you can use the induction hypothesis to rewrite your proof goal and then finish the proof. So this was a very fast overview, just to give you a glimpse, a taste of the proof language supported by Coq. So you have many different tactics to perform things as I have shown you: proof by simplification, proof by case analysis, proof by rewriting, proof by induction. Is that clear? Do you have any questions? Are you fine? Okay. Coq also has support for true and false from the logic, right? I have been talking about true and false as Boolean values, but you have a type called prop, which is a type of a proposition. So it's true and false from the logic. So the expression 3 is equal to 3 is of type prop. This predicate is also of type prop, right? Even if the proposition is not true, it's a proposition. So 3 equal to 4 is also an expression of type prop. And then Coq has specific tactics for dealing with true and false from the logic. So we have already seen, I have moved around some theorems, so this theorem should be deleted. I have already explained this. So here we're using some tactics that you have seen before, like intro, but there is a new one, which is the apply. That means if you have a proof goal and you have a hypothesis in your context, and the hypothesis is precisely equal to the proof goal, you can finish the proof by applying the hypothesis to the proof goal. What is more interesting concerning the apply tactic is what's called forward reasoning or backward reasoning. So suppose this situation, you have a statement that says that for any P and Q that are propositions, if P implies in P that implies Q, as a consequence of that, you have that Q must hold. So you have basically two strategies for proving this kind of statement. You can start from the hypothesis and deduce new facts until you reach a fact that is precisely equal to the goal. So it's called forward reasoning. You are moving from the hypothesis to the goal. So in this situation, when I write apply H2 in H1, I'm basically performing modus ponens. So if you remember what I'm saying, if you have P implies Q as a true statement, as a true proposition, and you have that P is also true, you can deduce that Q needs to be true. So when I perform this tactic, you note here that H1 changes from P to Q. So a new information is produced in the context. Actually, the previous one is also lost, but there are some tactics that you can use to keep some information if you want, if you need. And now you know that H1 is precisely equal to your proof goal. So you can finish this proof by using just apply H1. Another strategy for proving the same statement is to move from the goal to the hypothesis. So it's called backward reasoning. So in this situation, I'm applying the hypothesis to the goal. So if I want to prove that Q is true, and I assume that P implies Q, to finish this proof, what I need to prove is that P is true. So if I apply H2 to the proof goal, which is implicitly stated here, in this situation, the proof goal is going to be changed. And now I have a proof goal that is precisely equal to H1, and I can finish this proof. So this is something that you need to get used to when using COC, because as humans, sometimes some people are more used to forward reasoning. So that's my starting point. I want to produce new information until I reach the goal. But in many situations, it may be easier in COC to prove these statements using backward reasoning, because you have more theorems and results already proven in the library using this style. So that's something that takes a bit of time. Okay, it's now 3 p.m. local time. Should I continue a bit or should I stop now? It's up to you.
Maybe it's better to stop, give this half-hour break, and then we can finish to 3:30.
Perfect.
Okay.
Okay.
So thank you then, and let's take the scheduled break, and we'll see each other in half an hour.
Okay. Thank you. See you soon.
Yeah, the room will be still open, so you can remain here. I'll try to put some background music to see if it.
We're waiting for more. Thank you.
Okay. Thank you. So let me share my screen again. Right. So to summarize what I have been talking so far, so Cork has a functional language called Galena for specifying some behavior. It has a proof language where you can write statements to prove properties about this behavior, and then you can use these tactics to carry out the proofs. So to write proof scripts that show that the written statement indeed holds for that specification. And so besides the tactics I have mentioned in the beginning, so intros to perform, and the other ones to perform proof by simplification, by rewriting, induction, and case analysis, Cork has tactics specific for dealing with propositions. And we have stopped when I was talking about the idea of forward reasoning and backward reasoning. So to briefly cover, just to give you some glimpse of all the proof scripts, you may have conjunctions, right, in your statements. And there is a tactic called the split. That means if you want to prove the conjunction of two propositions, basically you need to prove each proposition individually. So when you perform this tactic, it creates two subgoals, and then you need to prove each one. And when you finish proving all subgoals, the initial statement is proven. If you have the conjunction in the proof context, so the conjunction is not in the proof goal, but in the context. So you have a hypothesis that involves a conjunction of two other propositions. You can use the tactic destruct to have two different hypotheses, one stating that A is true and the other one stating that B is true in this case. We also have disjunctions. So if you have a disjunction in the proof context, like here, you can use the same tactic, destruct, but in this situation with a different behavior as expected. That is, if you want to prove that some goal is true, and you have a hypothesis with a disjunction, basically you need to prove that this statement holds for each situation. So the situation where the first proposition of H is true, and the situation where the second proposition of H is true. So in this situation, when you destruct H, two subgoals are produced, and you need to handle each one separately. If you have the disjunction in the proof goal, like in this situation, so you want to prove that A or B is true, there is a tactic called left where you get rid of the right proposition. As you know, if I want to prove that A or B is true, it suffices to prove that A is true or that just B is true. So if I write, for instance, right, the proof goal is modified to keep on B. But in this situation, I want to keep the left part. So I write left, and I kept only the A, and then I can apply, in this situation, the hypothesis and finish the proof. In Cork, the logical negation is encoded as an implication. So there is this symbol here, which is a syntactic sugar for the definition not. And not is actually a function. So the logical negation is created using a function that receives a proposition A and yields the proposition A implies false. So briefly explaining this, you know that if P is true, the negation of P is false. And note that if the proposition is true, true implying false, the implication is false. If P is false, the negation of P is true. And similarly, if I have false implying false, this proposition is true. So the logical negation in Coq is encoded as this proposition. And it's important to understand this because when you are dealing with proofs where you have the logical negation, you probably need to unfold the definition of the negation to reach a situation where you have a contradiction in your context. I mean by contradiction that you have a hypothesis in your context that states false, for instance. That is what happens here. So in this situation, I have this proof where I have this hypothesis named contra, and it states that false is true, but it's a contradiction. So I can finish this proof by, there are many different ways, but one way is invoking a tactic called inversion and saying what is the hypothesis that the tactic inversion should consider. So in this situation, the proof finishes since I have reached a contradiction in the hypothesis. So as I said, suppose that you want to prove this statement, just to show you briefly, you need to unfold the negation, the definition of the logical negation. So here I'm using this tactic called unfold to unfold not. So when I do this, I get this the here, and then basically in this situation I'm using for the reasoning to produce the result I want. So I perform modus ponens, so I apply H to H2, and this produces as a new fact that H2 is false, and I have reached the contradiction I was seeking for, and I can finish this proof by inversion. As you have seen some previous proofs, most tactics in Coq have a variation called in. So you can perform the tactic in the proof context or in the proof goal. So you have just seen this unfold. So when you write unfold not, the standard interpretation is that you are unfolding the definition not the proof goal. If you want to unfold this definition in the proof context, you typically write unfold not in, and then you name the hypothesis in your context where you want the unfold to take place. So this is another situation, and here I'm unfolding the not in the context. True is a basic tautology. There is a tactic called apply I, which can be used to prove that true is true. Equivalence is just a syntactic sugar for, as expected, the conjunction of the implication on both directions. So for dealing with implication, for equivalences, you basically use the tactics that we have seen so far. So basically you unfold the if and only if as conjunctions, and then you perform the struct and split on the terms to prove what you want. And to finish the tactics for dealing with logical terms, we have invoked the existential quantification. And one way of proving something like this is to provide a witness. So suppose that you want to prove that there is a natural number n such that this equality holds. You can invoke the tactic exists, providing the value for the witness. And what it does, it substitutes the few occurrences of n in the proposition by the value provided to the tactic. And in this situation, you can finish the proof using reflexivity. And if you have the existential quantification in the proof context, you can also perform destruction. So in this situation, you can say, okay, I have this hypothesis saying that X is a M such that this holds. So you can say, okay, this holds for an arbitrary M, right? And note that the witness does not need to be a literal, right? It can be an expression, and then you can finish this proof as well. And to conclude this part, to go to the properly to the second one, I would like to also cover this idea that a same concept can be sometimes defined using Galena, so using functions. Sometimes a concept can be defined using logical terms, but also inductive definitions. That is something that I have not mentioned so far. Well, I have mentioned the use of inductive to create new types, but it's a slightly different application of inductive. So to illustrate this, recall the definition of even B. So even B has been defined as a recursive function that performs pattern matching on the argument n. We can also define the notion of evenness using a proposition. So here you have this definition even B prime that says that provided an n, this function produces a predicate encoding the notion that n is even. So a number n, a natural number n is even if if exists a k such that n is the double of k. So this is also a different way of specifying this property. And what is interesting, let me write some examples here. Suppose that you want to prove even B test 1. Suppose you want to prove that even B2 is true. You can prove this by simplification. So you have a function, even B in this situation is the function. So you can compute, so you can evaluate the function, and then you can finish this proof quite easily. However, if you are relying on the different definition of even B, so the one based on logical terms, if you want to prove that the proposition even B prime 2 is true, in this situation, one possible proof script would be to unfold, well, actually you can simplify, so you can compute the function even B prime. Note that even B prime is a function. Sorry, not compute it, you need to unfold even B prime. And then you are exposed to the existential quantification, and then you can provide the witness and then perform the necessary computation to finish the proof. So note that depending on how you specify the property, the proof style will be different. Okay. Actually, you can prove that both definitions I have shown are precisely the same. So in terms of the meaning, so you can, I'm not going to explain the details of these theorems and lemmas, but basically they are defining intermediate results such that in the end, you can say that the function even b applied to some number n, this function yields true if and only if the logical definition holds. So based on these previously defined lemmas and theorems, you can prove that this equivalence holds. And we say that in this situation, that the functional definition of even b reflects the logical proposition of even b prime. And to show this reflection, it's interesting because in some situations you want to have the functional definition, in other situations you want to have the logical definition. And just to illustrate some situations, if you have the functional one, you can, for instance, perform computations, you can perform simplifications on the terms, whereas the second one is more interesting to perform rewriting, for instance. So there is in Coq the equality, the Boolean equality, which is a function. So the Boolean equality of natural numbers, this is a function. And there is the notion of equality, not in terms of a function, but in terms of logic, of a logical predicate. And if you have this, you cannot perform rewrite, but if you have this, you can. On the other hand, if you have this, you cannot perform simplification because this is not a computable definition, where in this situation it is. So proving that a functional definition reflects a logical concept is something that is quite common, and Coq actually provides some libraries for making easier the process of proving that these equivalences hold. And there is also a third alternative that is defining properties inductively. This is very useful when you have a concept where the computation of this concept does not necessarily terminate for any possible input, but regardless of this, you want to encode the concept in the framework. So this is quite common, for instance, if you are modeling notions of reachability in a graph where, well, these you may have loops, and in some situations it may not end the computation. So you can encode these using inductive propositions. So here there is a sketch for, not a sketch, well, the proper definition of how to encode the notion of a number being even using inductive definitions. So here you are, this construct is saying that EV applied to 0 is a valid proposition. So it's a proposition that is true. So I'm providing evidence that 0 is an even number. And here I have a different constructor that provides me a statement that enables me to generate new facts based on previous ones. So basically it says that for any natural number n, if you have the evidence that n is even, you can say that the successor of this number is also even. So suppose that using this definition, you want to prove that 4 is even. In this situation, one possible way of proving this is using backward reasoning, on where you apply these constructors to reach the basic evidence that you have in the in the inductive definition of evenness. And you can also prove that these 3 definitions are precisely the same in terms of their meaning. I'm going to skip the proofs because my intention is not to explain the details here, but just to show that for any natural number n, this proposition EVN holds if and only if this one holds as well. So this is an interesting topic. Unfortunately, due to the time, I'm not going to say anything else about these at this moment, unless you have questions. But when you're creating a specification, you typically need to think about how you are going to encode your, how you're going to specify the behavior of something you're modeling. Okay. Well, that ends the first part. And now, assume that you have this basic idea of what is Coq and its languages. I would like to show you a more interesting example, a more practical example. But before this example, suppose that another interesting application, possible application of Coq would be, for instance, providing semantics for the diagrams Anna explained in the first lecture. So she mentioned during her talk that trying to prove the properties using model checkers, typically this does not scale. And one thing that we can do, and we plan to do, is to derive the semantics automatically of that models and of that sentences using some proof assistant or theorem prover. As Anna mentioned, we are going to use Isabel, which is a different tool. But basically the idea is to generate a specification that encodes the semantics of that models, of that diagrams, of that sentences, and then you can rely on proof scripts that in some situations can be, the proof can be performed automatically using some theorem provers, but in some situations you will need some user intervention to write these proof scripts. So there is a downside of relying on some user experts, but there is the positive aspects of being able to deal with more complex examples, since you typically face these scalability problems when considering the typical model checkers. But that's one possible application of Coq, for instance. But now in the second part, I would like to show you an example that may be more familiar for you in the context of algorithms. So when learning data structures, you probably have studied dictionaries, which is, conceptually speaking, a mapping between keys and values. And what I'm going to show now is how to use Coq to first specify the concepts related to a dictionary, then define an implementation of a dictionary. So first you define the abstract data type dictionary, then you provide a concrete implementation, and finally you prove that your concrete implementation satisfies the properties you have specified. Okay. So again, if you have any questions, please do interrupt me. And here I'm importing many things from the standard library. So these keywords here are saying that I'm defining, I'm creating kind of an interface of a new abstract data type. And this type is called a dictionary. Here, I don't have, I'm not considering a polymorphic dictionary, what would be possible, but I'm not doing this to keep things a bit simpler. So I have a key in this dictionary, and a key is a natural number, and I have a value, and the value is a string. So my dictionary is mapping numbers to strings. Note that in these two first definitions, I use the keyword definition, whereas here I use a different keyword called parameter. So basically this keyword is saying that I'm not giving too much information at this moment about this definition. This should be done when you are defining the data structure, so the implementation of this abstract data type. So I'm saying basically that a dictionary is of some possible type. So type is the collection of valid types. I'm not being specific here of how this dictionary is going to be implemented. I also say here that when creating an instance, an implementation for this abstract data type, you should say to me what is an empty dictionary. And obviously, this definition should have a value of type dictionary. After defining these elements, I can write the interface from the perspective of programming languages, from oriented programming languages. And I mean here the interface as the operations that can be performed on this type. So using functions, since Galena is a functional language, I'm saying here that you have 5 available operations on this type. So you can clear a dictionary, you can check whether a dictionary is empty, you can ask the size of that dictionary, you can insert a key and a value into a dictionary, and you can search whether a given key belongs to this dictionary. And here I'm using this option. If I'm familiar with Haskell, this would be the maybe. So the output of this, the value yielded by this function will be none if there is no key of this value in the dictionary, or some v if there is. Okay, so far, you could say, okay, I can write something like this in Java, for instance. I can create an interface and state the list of operations that the dictionary abstract data type support. But now it comes the part that's different. I have here different statements that are encoding properties about a dictionary that should hold in any implementation of a dictionary. So at this level, the properties are axioms, and when I define a data structure implementing this ADT, I will need to prove that these statements hold for that particular implementation. So I say here that for any dictionary, if you clear it, and then you check whether it is empty, the result should be true, okay? So basically you are saying something about the correctness of the clear implementation. You could also say that when you clear a dictionary, the size of the resulting dictionary is 0. So you have no elements at all. It's empty. You can also say that if a dictionary is empty, this dictionary D is exactly the definition of an empty dictionary if it's an if and only if. You can also relate the notion of the function is empty with the function size. So if for any dictionary D, if the dictionary is empty, its size is 0. You can say something about trying to search keys in an empty dictionary. So if a dictionary is empty, if you try to find anything in the dictionary, the outcome will be always none. So the dictionary is empty. You can write statements saying something about the insert operation. So here it says that if you insert the pair KV into dictionary D, and after that you try to find the key K, the output will be precisely the value you have just inserted. And you can also state that if you are inserting a pair in the dictionary, in a situation where the key was already there, I'm saying that the size of the dictionary after the insertion is going to be the same. So what I'm trying to encode here is that if you have a dictionary where K is already there and you try to insert a new pair, what the insertion does is it updates the mapping, right? So that's the expected behavior of any valid implementation of dictionary, considering this definition. However, if you are inserting a pair where there is no key K in that dictionary, well, the insertion will increase the size of the dictionary by 1. So I'm going to process these definitions, and now I have the formal specification of the dictionary and the expected properties formalized. And now comes the part where we're going to define the data structure. So here I'm creating a new type called a dictionary PST that implements the notion of a dictionary using binary search trees. So you could be using lists or some more sophisticated binary search trees like red-black trees and, well, what you have studied in your data structure course. So considering binary search trees, I define a new inductive type called binary tree. I say that there is an empty tree, which is created with the constructor bnil. It's a polymorphic binary tree. I also have a constructor that creates a new tree from a value and the left and right subtree. There is some comments here to say to Coq that when I use these constructors, please try to infer automatically the type of the binary tree. Don't rely on me saying that. So these comments here are basically saying that the type of the binary tree is implicit. So now I repeat the definitions of key and val as before, but note that here the dictionary and the empty dictionary is no more a parameter, it's a definition. So it's something concrete. And here I say, okay, the dictionary is going to be represented as a binary tree of pairs. And each node of the tree holds a pair associating a key with a value. And the empty dictionary is the new is a value created with this constructor. And after providing these basic definitions, what I need to do is I need to provide an implementation for the functions, for the operations that have not been defined. So not been defined, you had just a signature, now you need to provide the body. So for instance, I'm saying here that the function clear just uses be nil. The function is empty, checks whether D is be nil. If it's the case, it yields true, otherwise it yields false. The function size is a recursive function. It performs pattern matching on the dictionary. If the dictionary is be nil, so it's the empty tree, the return is 0. Otherwise, if the dictionary has a pair, a left subtree and a right subtree, the size of this dictionary is going to be 1 plus the size of the left and right subtrees. So sizes return the number of entries in the dictionary. Here is the definition of the insertion. So actually what we had so far was just a binary tree. The insertion is a function that is guaranteeing that this tree is actually a binary search tree. So for each node, the left elements comprise keys that are less than the root, and the right one is greater than or equal to. So the insertion is also a recursive function. If the dictionary is empty, it creates a tree with the pair, and the left and right subtrees are empty. If the dictionary is not empty, it checks for this pair if the first element of the pair is equal to the key I'm inserting. If this is the case, I just update the value. So I keep the left subtree and the right subtree the same, and I update the pair of this node. If this is not the case, if k is less than the key of the current root, I recurse to the left subtree. Otherwise, I recurse to the right subtree. So that's a pretty standard way of implementing the insertion of binary search trees. And there is a very similar definition for searching in a binary search tree. So suppose that now I try to finish my definition of a dictionary as a binary search tree. If I try to do this, I get this error message here. Okay, in the specification of a dictionary, I had a field called clear empty. And if we go back, this name refers to this axiom. And what it's saying here is that I expect you to provide an evidence that this axiom holds in the provided implementation of a dictionary. And Coq will only allow me to finish my definition when all the stated properties have been proven. So what I need to do now is to create theorems to prove the previously stated predicates. So now it comes the proof language, so the tactics. So I will need to use the tactics that I have mentioned before to prove that each of these propositions hold in this concrete implementation of dictionaries. So I'm using universal quantification, simplification, and reflexivity in this case. In these other situations, in this other theorem, I also have a very similar proof script. In this other situation, I have logical terms. So I need to perform unfold of the if and only if. This will expose the conjunction. So if I need to prove that P and Q, that the conjunction is true, I need to prove separately that P holds and Q holds. So, and then it comes here, I'm performing a proof by case analysis. So basically I'm saying, okay, consider two situations. The first one, the dictionary is empty, the dictionary, which is a tree, is an empty tree. And in this other situation, suppose that the dictionary is an arbitrary tree that is not empty. This discriminate tactic is somehow similar to inversion. This would also work here. So I'm not going to explain all the details of the proof scripts, but just to illustrate to you that now I'm using the tactics that I have mentioned before. So I'm performing, I'm manipulating logical terms, I'm performing simplification. Rewrite is going to appear in the next proof. So I'm trying to prove something by rewriting, by simplification, by case analysis. In more complex theorems, I will need to perform induction. So all that tactics come to place to prove these statements. I think, let's see which one I'm going to explain a bit more. I'm going to explain a bit more details, in a bit more detail this one, because I want to show you something, I want to say something about proof automation. So in this last theorem, it states that if I want to insert a pair in a dictionary, and there is nothing mapped to K, the insertion is going to increase the size of the dictionary by 1. So that's the intuition behind this statement. So what I need to do here is a combination of induction with case analysis. So in the basic situation, the tree is empty. So when the tree is empty, if you recall the definition of insert, when the tree is empty, you basically create a tree with a root with the pair you are inserting. So if I simplify this term, I will get that this will become a tree with a single element. And when I simplify size, this term will become 1. This term becomes 0 because the size of empty tree is 0. And 0 plus 1 is 1. And I'm left with this trivial equality that I can prove using reflexivity. When the tree is not empty, note that here I have 2 induction hypotheses. Now I need to perform case analysis. So if I'm inserting a pair in the tree, I have 3 cases. The case where the key is already in the tree, and I'm going to update the mapping. But this situation will render a contradiction because note that I'm assuming that the element, the key, is not there. There is a second situation where the pair is inserted to the left, and there is a third situation where the pair is inserted to the right. So basically what I have now are tactics for dealing with these 3 cases. So I perform first a case analysis, assuming that the key is there. In this situation, I reach a contradiction. so something that does not make sense. Here, I'm going to assume that the insertion goes to the left, recurses to the left. And there is the other situation where the recursion, the function recurses to the right. And in each situation, I will use this induction hypothesis to finish my proof. And I also need to, in this proof script, to rely on some properties of natural numbers, because I want to perform commutations of these terms to finish my proof. So as you can see, if you want, your proof script can be too low level. So you are indeed manipulating the bits of the proof goal until proving that it holds. What Coq also provides you is with some meta tactics. So in tactics, you could say that they are high order tactics. So you have tactics that receive as input other tactics. And you also have this interesting language called LTAC that you can create decision procedures that will automate some kind of proofs. And there is one important thing to say. Coq requires that all functions terminate. So any recursive definition in Galena should terminate. However, Coq does not require that a definition in LTAC always terminate. So when you are encoding decision procedure, you have less restrictions, and you can even write some decision procedure that will not terminate. Well, I think you are not going to want this, but you can. So here, to almost finish, you have the same statement, right? And note that this proof script is more concise than this one, what is nice. However, you lose you do not see anymore the step-by-step evolution of the proof goal. So there is a compromise here. You can, using this automation language, you can write shorter proof scripts, but the proof scripts may be less readable by a human. It becomes harder to understand what's going on under the hood. So just to show you some, say something about this, the proof starts similarly. So I'm performing induction on the dictionary. And in the basic case, I'm using this tactic called auto. If you write debug auto, you can see what is going on. So this tactic auto is a decision procedure that will try to apply some tactics, and if they fail, it tries another one, and you have some control regarding which tactics auto is going to apply, and you also have control regarding the number of nested applications it's going to do. So in this case, note that it was trying different things, and then this tactic here, which is basically reflexivity, finish the sub-goal. And the other three cases is dealt by a single command. So note that you need to prove this, and by executing this very long command, it finishes the proof automatically. And what is going on here is that instead of separating the tactics using a dot, I'm using a semicolon. And it means that each tactic is going to be applied to all sub-goals at once. So what the intuition behind this big step is, I'm destructing the hypothesis to consider the three situations I mentioned before. I'm performing all possible simplifications in the proof context in the proof goal. I'm performing all possible rewrites I can using hypothesis H prime. I'm trying to finish some sub-goals using discriminate, which is similar to inversion. Then I'm trying to rewrite this everything that's possible considering these other hypotheses. I'm trying to apply the inductive hypothesis in H, simplify the sub-goal, rewrite H, and in the end, I have this LIA tactic, which encodes a decision procedure for a subset of arithmetic expressions. And by invoking LIA, I finish these proofs without the need of relying on more detailed information like I'm now using the property that they add the associative and things like that. So with this big step, the same proof is finished in a more concise way. And now, since I have defined the body of all functions, and since that I have proven that all properties defined in the specification hold in this implementation, I can finish my definition. So it's much more stronger than if you were writing this in Java, for instance, and performing a number of tests. Here, I'm not checking whether the properties hold in some cases. I'm showing that the property holds in any possible situation. And to conclude this talk, one thing that you can do using Coq is that typically you wouldn't expect the system to be implemented using Coq. Coq is the language, it's a collection of languages for specifying for formally specifying the expected behavior, for proving that an implementation satisfies this behavior. But in the end, you will probably want to generate some code from the implementation. So the easiest thing that you can do, and you have native support for doing this, is that you can extract Haskell code from the Galena specification. So if you execute these commands, a file with a Haskell code is going to be generated. And in the Haskell code, you will not have the theorems, you will not have the actions. What you will have will be the concrete implementation. So the functions and the types. And then you can rely on more specific compilers that will hopefully optimize this code. Okay. You can even go to other languages, like languages such as C, using a collection of tools. So in the Coq, let's say, collection of tools, you have the possibility, for instance, to derive a formal specification in Coq from a C code and use Coq to prove the properties of interest, what would in the end give you some confidence that that C code is correct. You could use C compilers that have been proved correct in Coq. And that's the idea of the DeepSpec project, which is to provide a stack of tools to develop software and hardware with strong correctness guarantees. So I think I'm going to stop now I think I have shown you everything that I have planned. Thank you very much for your attention. And then I would be glad if you have any questions. Thank you.
Thank you very much for the presentation. So the floor is open for questions. Okay, let me ask one to break the ice. So you've shown us a demo going from some very simple things to right, some implementation, right, a dictionary. What is the learning curve, right? So how long does it take for somebody to go from this tutorial to actually being able to verify a data structure like the one you presented?
Okay. Well, the
This is meant to
learning curve.
encourage people to take it
Yeah.
up.
Yes, yes. Well, I will speak about my personal experience on learning Coq. So I always had the interest in learning more about theorem provers and proof assistants. That's something that I have not had the opportunity to use during my PhD. And then I started reading the software foundations, basically the first book, so logical foundations. I would say I spent, because it's not just a book with, you have many exercises. So I would say I spent about 2 months going through the book, doing the exercises, but also teaching and doing many other stuff. And then I attended the summer school. I spent 2 weeks studying hard. And I would say that after this period, I was ready to write an example like this one I showed you. If you want to pursue more complicated things, I think it will depend on your background. So there is lots of things in Coq for dealing with separation logic, for instance, and how easy is it going to use this material depends on your theoretical knowledge on separation logic. So you need to know the basics of Coq, but also some other concepts that are independent. And the Software Foundation series is very nice in this sense because you have different books covering the basics of different perspectives. I think, let me share you just a second. I think I'm not able to share anymore. I think now, not yet. But well, if you go to this link, you can do this by yourselves. You are going to see that you have 6 books. So you have the first volume covering what is called the logical foundations. So volume 1 is basically what I have shown you in part 1. You have volume 2 speaking about Hoare logic, Hoare triples, and how you can use Coq to encode new programming languages. So you want to use Coq to represent a new functional language, a new imperative language. That's the volume 2 is focused on imperative languages. You have volume 3, which has this idea of using Coq to prove that functional algorithms are correct. So volume 3 is aligned to part 2 of this talk. You have another volume covering quick check, which is the Coq's version of quick check. So if you know Haskell and you know quick check is quick check for Haskell. And you have volumes 5 and 6 covering that idea I mentioned of using Coq to reason about C programs. So you should probably first read volume 6 about separation logic, and then understand how this verifiable C tool has been developed to reason about this. Instead that, the recommendation of the authors is that each volume would be covered in one semester, right? So there are different paths depending on what you want to do with Coq. But I would say if you work hard, a couple of months would be enough to get you started.
Okay, thank you very much. That was a very good set of resources and good encouragement. Any other questions?
I have a question. So that was very nice, Gustavo, very interesting. You mentioned that, if I remember correctly, you mentioned some C compiler that has been verified by Coq.
Yeah.
So my question is, how big can we work with Coq? And a C compiler is pretty large. So is it, is it at the top end of something that's manageable by Coq, or is it easy to do? I would like to get an idea of how large we can go.
Perfect. I will try to share my screen. I cannot share my screen yet. I'm not sure whether Tiago is here. Maybe
Tiago is not here. He had to leave.
No. Right. Is some volunteer here that could grant me access to share my screen? Because
Supposedly.
Try not yet. Well, I will do the same. I will paste the link in the chat. So if you can open, Sergio, please, and everyone. This is an image from the DeepSpec project. So it's a very challenging project. And what you see in this project is the universe of things that they are formalizing using Coq. So it goes from hardware up to web services. So you have a collection of different things formalized. So briefly speaking, you can reason about a lot of things, provided you have the expertise and the time to do this. So as I remember from the summer school, they have special groups working on different perspectives. So they have a group, for instance, working on hardware. They have a group working on developing certified kernels for specific operating systems. They have people working on CompCert, which is the C compiler I mentioned. So in summary, you can reason about many things. It can become really large.
That's very interesting. And you can also reuse some of this code if you want to start something that's related to some that has already been done. That's a very impressive list of things that can be done. As I live in the model checking world, so for me, every bit is important. So I know that this is not the case here, and it's nice to see that, because when I started learning about theorem proving, I saw all of those theorems like you've shown, that the number plus 0 is the same as that number and all of that. And I'm like, oh God, if I have to do all of it, I will never get off the ground, right? So I'm glad to see that it's not. In this instance, your dictionary example was very interesting because it doesn't deal with n plus 0 equals n. So it's nice to see that you can actually do a lot of sophisticated stuff, because one of the problems we have in model checking is that every time you grow the example, it just explodes on you. And from my perspective, it would seem that it would explode even faster in a theorem proving world, but I'm glad to see that this is not the case. So yeah, thank you. That's very interesting to see that all of this can be actually verified, and a lot of interesting things can be done with this tool.
So thank you very much again. Any other questions from the audience? Okay, so then I think we should thank Gustavo again for wrapping up the first day and the day of lectures of the school. I think we will all reconvene tomorrow at 8:30 for the official opening of the symposium, right?
Yes.
Yes, I guess so.
Right.
Okay. Well,
Okay,
then,
Okay.
so yeah, thank you all. And Tiago left me to say goodbye to everybody. So goodbye, everybody.
And see you tomorrow.
See you tomorrow.
bye-bye.
Bye-bye.